Hello and welcome to Mrs. Law's class. In this lesson, I'm going to show you the binomial theorem. Now, before I do that, we're going to take a look at a little investigation so that you can see where the binomial theorem actually comes from. So, first, we're going to expand and simplify each of the following powers of the binomial a plus b. So in the first one, we see that a plus b is all in brackets to the power of 0, and anything to the power of 0 is equal to 1. All right, so next we have a plus b to the power of 1. So it's going to still be a plus b. All right, so expanding a little bit more, we now have a plus b squared. So if we distribute, we're going to get a squared plus 2ab plus b squared. All right, so now we have a plus b cubed. All right, so if you want to multiply the quadratic that we had from before times a plus b, then you're going to get a cubed plus 3a squared b plus 3ab squared, and then plus b cubed. All right, so now we're going to take this quartic that we have, and we're going to multiply by another a plus b, so we get a plus b to the power of 4. So I've already done this, and if you do multiply it out, you're going to get a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed, and then plus b to the power of 4. Now, if you notice to my right, I have Pascal's triangle written as a second column. So if I list out Pascal's triangle, so recall it's going to be 1, and then 1, 1, 1, 2, 1, 1, 3, 3, 1, and then 1, 4, 6, 4, 1. So if you take a look at Pascal's triangle and the coefficients of the binomial that I had expanded, you will notice that the coefficients of my expanded binomial are the same as the row in Pascal's triangle. All right, and that is not by coincidence. So knowing this, we can now predict the expansion of a plus b to the power of 5. So if we list the next row in Pascal's triangle, we know it's going to be 1, 5, 10, 10, 5, 1. All right, so we do notice some other things. We notice that the a to the power of 4, notice that the exponents are decreasing, but the b, their exponents, is increasing. So it starts with b to the 0, 1, 2, 3, and 4. So using that pattern and knowing Pascal's triangle, we can now expand a plus b to the power of 5 without actually having to multiply another binomial. So this would be a to the power of 5. Notice the pattern. And then plus 5. So now it's going to decrease a to the 4. And then we're going to start increasing our b's. So times b. And then plus 10, a cubed, b squared, plus another 10. A's are decreasing by their power, so a squared, b cubed, plus 5, a, b to the 4, and then plus b to the 5. All right, so this brings us to the binomial theorem. So the binomial theorem is a method for expanding an expression of the form a plus b, all in brackets, to the power of n, where n is a natural number. Now, recall that Pascal's triangle, it can be written in the form NCR, and that's from a previous video if you need to watch that. So this means that the numerical coefficients of a binomial expansion can be written using the NCR notation. So this fact and the pattern of the powers in successive terms leads to the following theorem. So the expansion of x plus y to the power of n, where n is a natural number, is given by nc0. So that's the first number in Pascal's triangle. And then we have x to the n, and then y to the 0. Plus nc1 is the next value in Pascal's triangle. And then we have x to the n minus 1, because the exponent is decreasing, and the y exponent starts increasing. So we have y to the 1. Plus nc2, and then x to the n minus 2, y to the 2. Plus, and then dot, dot, dot. So this keeps going. And the second to last term will be n minus 1, x to the power of 1, y to the power of n minus 1. And then the very last term will be ncn, x to the 0 now, and then y to the power of n. All right, some observations. So notice that the powers of x, okay, they decrease, like I said, and it decreases from n to 0. So notice that n is the exponent in the binomial. The powers of y, notice that they increase from 0 to n. Okay? The expansion contains n plus 1 terms. So notice if we go back, if it was power 0, we have 1 term. If it was power 1, we had 2 terms. Notice it was power 4, we actually had 5 terms. Okay. The numerical coefficients follow Pascal's triangle. So that's the fourth observation. The exponent of y in the expansion is the same as r and NCR. Okay, so for example, if we have NCR, x is to the power of n minus r, and then notice that y is to the power of r, so that these are the same. So that's helpful when you're writing and expanding. The exponent of y in the expansion is also 1 less than the term position. So for example, let's say that we're looking for the pth term. I just randomly chose a letter of the expansion. X plus y to the power of n, and this would be n c p minus 1. Okay, so let's say we're looking for the 8th term, and this would be nc7. Okay, this would be x to the power of n minus p minus 1, and then y to the power of p minus 1. And then the last observation is the sum of the exponents of any term of the expansion is always n. So what this means, I'll show you back here. If I add the exponents, we have 4 plus 1, notice it's 5. 3 plus 2, that's also 5, and so on. Okay? All right, so let's take a look at some examples. All right, in this first one here, we have x minus 3 all to the power of 4. So we know that it's a power of 4. That means our n is 4. So we're going to start with 4c0. And then we have x, that's our a value. Or you can call it our a or x value. And this would be our y value. Don't forget to include the negative 3. Or the negative sign, I mean. So we have x to the power of 4. Negative 3 to the power of 0. And then now we have 4c1, and then it becomes x to the power of 3. We're going to decrease, negative 3 to the power of 1, plus 4c2, x to the power of 2. We're decreasing the x exponents, and then negative 3 to the power of 2. We're increasing the negative 3 exponent, plus 4c3, x to the power of 1, negative 3 to the power of 3. And then the last one is 4c4. We know to stop because it's 4c4, x to the power of 0, and negative 3 to the power of 4. All right, so then if you have Pascal's triangle memorized, you can just write that down, okay? Or if you need to type it out, you can also type it out. So this will be 1 times x to the 4 times 1 plus 4x cubed times negative 3 plus 6x squared times 9 plus 4x, and that's going to be negative 27, and then plus 1 times 81. Okay, so last step here, I'm just going to simplify everything. I have x to the power of 4, and so this is actually going to be 4 times negative 3, so it's negative 12x cubed plus 54x squared minus 108x, and then plus 81. All right, let's take a look at one more example. So here we have two variables, 2x and the y, to the power of 3. So we're going to start with 3, c0. And then we're going to have 2x in brackets cubed, y to the 0, plus 3c1, 2x, and it's squared because it's decreasing, y to the 1, it's increasing, plus 3c2, 2x to the power of 1, and then we have y squared, and then the last term is 3c3, 2x to the 0, and then y cubed. All right, so simplifying this, we get 8x cubed. Don't forget it's going to be 2 cubed, and also x cubed, plus 3, and then this will be 4x squared times y, plus 3 again, because that's Pascal's triangle, right? 1, 3, 3, 1. And this will be y squared, and then plus, we'll just write y cubed here. So simplifying one more time, we get 8x cubed plus 12x squared y plus 6x y squared, and then plus y cubed. So that is how you can expand any binomial by using the binomial theorem.